So, this is the fifth lecture on second module, where we are talking about applications of dynamics of offshore structures. In the last lecture we discussed about how to linearize the drag force we already said that the drag force of Z of t after linearization can be given by Ci plus Cd root of 8 by pi sigma Vx and Vx and Ca as components of Cm and Ca. We have also found out how to find Morrison forces on inclined members in the last lecture. In the present lecture we will talk about the introduction to earthquake forces, and we will also start introduction to the dynamic analysis for articulated towers. We have already seen one example in the last lecture where we did dynamic analysis for jacket structures. We will talk about the formulation of the problem of our articulated towers, and then we will see some results of the dynamic analysis done for ATs in this lecture. So, we already know in case of offshore structures two important forces are applied. One is from the wave plus current, and of course from the wind, and also the earthquake forces. If we do not consider the aerodynamic response, then wind force may not be considered. Of course, the wave force will create a lateral force, or the wave effect will create a lateral force on the member, plus of course the earthquake forces are got to be definitely considered in the offshore structures, whereas in land based structures this can be an optional criteria to add the earthquake forces to the lateral forces coming on the system, whereas in offshore structures, as we have seen in the previous module lectures, it is mandatory that I must consider the earthquake forces coming on the system. Now, the moment I say earthquake forces, if I got a platform which is resting on the seabed, then earthquake forces can be directly applied onto it. Then earthquake forces can be directly applied onto the members. If the platform is compliant and anchored to the seabed, let us say for example by teethers, then earthquake forces are applied indirectly to the members. First we will take an example that how do we apply the direct forces, then we will speak about this in this lecture, and then we will talk about the dynamic analysis of mathematical model on articulated towers in this lecture and consequently the next lecture. Now, there are some basic assumptions what we make when we working out the forces on earthquake force on offshore structures resting on the seabed. We say the ground acceleration u double dot g basic assumptions what we make in case of applying earthquake forces on structures or offshore structures resting on seabed. We say that the ground acceleration which I say u double dot g occurring during earthquake is a non-zero mean ergodic Gaussian process. We all understand that earthquake is a random phenomenon. So, whenever there is a random phenomena applied on loading, we must use the statistical tools to find out the equivalent force as applied. So, generally people do spectral analysis for that. So, there is a basic assumption in my loading that is a non-zero mean. What does it mean is, if you got a plot, whatever may be the however may be the variation, if the positive and negative amplitude sum brings the mean to 0, I call that process a zero mean process. But when the positive or the negative amplitude is higher and my mean does not come here but shifts either upward or downward, I call that as a non-zero mean process. So, it means the positive and negative amplitude of the random time history of the force is not equal with respect to any mean activity. So, it is a non-zero mean process, and of course in statistical terms the process is ergodic and we can apply a Gaussian rule to this. So, we say it is an ergodic Gaussian process. Therefore, literature recommends a step by step time history analysis for this. For such cases. So, on the other hand, the dynamic analysis of systems of platforms under earthquake loads is usually carried out in time domain. But the autocorrelation function of the acceleration record you have an acceleration time history record u double dot g, which is a time history. The autocorrelation function of the acceleration record is reasonably small. For time separation of 20 to 50 seconds. It has been estimated from the existing records that the autocorrelation function is reasonably small for this time separation, and hence one can do spectral analysis. So, one can do a spectral analysis in this case. The moment I say spectral analysis, then I must define a spectrum based on which my earthquake loading will be computed, or the energy applied on the system under earthquake loading will be computed. So, in offshore structures, people have used the famous Kanai-Tajimi spectrum. Some people call this power spectrum, so I am writing it in brackets, which is given by Kanai K in 1957 for seismic characterization of the ground, published in Bulletin of Earthquake Research, Institute, University of Tokyo, volume 35, 3082 355, sorry 325, 3082 325, and subsequently given by Tajimi in 1960. A structural method of determining the maximum response of a structure during earthquake. Proceedings of the Second World Conference on earthquake engineering, held in Tokyo and Kyoto, volume 11. So, based on these two references, a power spectrum was proposed and referred in the literature as Kanai-Tajimi power spectrum, which is quite often being recommended for obtaining the earthquake forces on offshore structures. Again, remember, we have got two options. The offshore structure can rest on the seabed where earthquake forces are imposed. We do an analysis. Offshore structures can be anchored to the seabed using tethers or any cable system, then again earthquake is applied on the seabed, how will it transfer. So, we are looking at the option A where the offshore structure is resting on the seabed. So, the spectrum is given by S U double dot G U double dot G of omega, where omega is the frequency content of this, so I want to prevent or protect the directionality. So, I take the mod value of this, where S0 is a constant which represents the strength of the disturbance. So, here people do a factor that if the offshore structure is not directly resting on the bed which is subjected to a seismic action, then S0 can be a factor which can be multiplied to the power spectrum of Kanai-Tajimi to find the reduced effect of the spectrum on the superstructure. So, S0 is a constant which represents the strength of the disturbance applied onto the structure. If the structure is resting on the soil or on the seabed directly, usually researchers take this as 1. Omega g is the characteristic ground frequency. Remember, I am using the term characteristic, it has got a specific meaning in statistical analogy. Okay. For example, FCK in concrete is characteristic compressive strength of concrete. It means it has got a specific definition. What do you mean by a characteristic strength? Okay. In statistical terms, I am looking at this because I am assuming that this is a non-zero Gaussian process, okay, in statistical terms. So, omega g is a characteristic ground frequency ranging from 5 to 6 pi radians per second, that is the range, ranging from 5 to 6 pi radians per second. Of course, omega is the frequency content of analysis in the spectrum, and gamma g is the characteristic ground damping. Ratio. So, ratio considered for the specific site or platform, whatever you want to take, which can generally vary from 0.6 to 0.7 for hot soil. So, for a given characteristic ground frequency of any value for a different range of omega for a specific characteristic ground damping ratio, I will be able to plot the spectrum. If I assume any disturbance by number, it is nothing but a constant, I plot the spectrum, that will give me the energy where I am going to apply onto my platform. I will remove this. Now, once the spectrum is known, and lateral forces arising from wave, current, etc. are known, then one can account for the wave structure interaction in the analysis. We will quickly see very briefly how the equation of motion can be written in this case. I will remove this. Now, here there are some basic structural idealizations we do. Let us see what are they. 1, earthquake force is applied in the horizontal direction in the horizontal direction assuming that C bed movement is horizontal. So, in the vertical direction we do not impose, okay. That is an idealization what we do in the analysis. I will come to this explanation why it is so later. Let us try to understand that the C bed movement is considered to be horizontal. The moment I say C bed is moving with respect to some time history, then one can wonder whether the water body will also move. The second assumption is the earthquake forces does not move the ocean horizontal, okay. It is very important. 3, obviously when I place a slender cylinder in a fluid structure medium, when the cylinder is very slender, the cylinder will also what vibrating, and this vibrating motion will also cause some additional forces because of this vibration, okay. The third assumption is pertaining to that all slender members will not produce appreciable amplitude of vibration So, what does it mean? This says that the radiation damping can be neglected. That is the counter effect of this assumption. So, having said this, let us pick up a slender member and write the equation of motion for this under earthquake forces. Let us say at any section Z from here, let us say the member has moved by u. Of course, there is a displacement of the center line of the member because of the UG displacement, because I said it is C bed movement. So, I now say the total displacement is sum of the ground displacement plus the displacement of the body because of the lateral forces action. Now, interestingly, Ku will be the restoring force associated with the stiffness of the member, which accounts for only u. Okay, be careful, it is not ug, it is the stiffness of the member only for the displacement u. ug plays no role in stiffness. And of course C u dot is the damping force. Again a function of u only. Okay. This can be okay. Having said this, we can now say m u total double dot plus C u dot plus K u is f of t. That is my equation of motion 1. So, equation 1 is the equation of motion of the cylinder under the combined action of u double dot g plus u, that is u is because of displacement by the lateral force and u double dot g is the accelerated force, or simply you can say ug, displacement because of the seabed movement. We already know f z of t, I am replacing it here from our previous expression, which can be given by Cm of v dot minus u double dot total. There is a confusion here, I am talking this v dot as acceleration, u double dot is acceleration total because of the seabed movement and the acceleration of the cylinder under the lateral forces. Okay. So, that is why there is no double dot here, because I am using the same convention as I wrote the equation in the previous lecture with v dot. Okay. Plus Ca v dot plus Cd root a by pi. I am looking for a linear drag on a slender cylinder, I am talking about slender cylinder here, sigma r statistical property v minus u dot. Okay. V is again a velocity here, it is not displacement, and we already know that this Cm this Cm accounts for pi d square by 4 rho w Cm and the Ca accounts for rho a, is it not? We already know this. Okay. And the relative velocity now, which is r, as you see here as a subscript, is v minus u dot of t. Okay. So, as a first approximation, this scheme is going to be iterative. When you use a time domain analysis solution, this will be iterative. So, going to be iterative as a first approximation because in the first value you will not have sigma. Okay. because you will have only one set of values. When you iterate you will get more and then you can use this, but initially sigma r is taken as sigma v directly. Do not impose the relative value here to start with, okay. To start with no relative imposition is done. So let me rewrite this equation again, okay. M u double dot total plus C u dot plus K u is f z of t. I am saying this as M u double dot plus u double dot of g plus C u dot plus K u as Cm is equal to Cm v minus of u total, u double dot total, which is the ground displacement acceleration plus the cylinder acceleration. Okay, let me do it here, plus Ca of v dot plus Cd 8 by pi root sigma v, that is what my initial approximation is, just now I said this, multiplied by u total is here. So I should say v minus u plus u dot. Any questions here? I rearrange this term slightly in a different form. Any questions here? I rearrange these terms, I should say rearranging so M plus, of course this is on the right hand side, I should say equal to, this is RHS, this is RHS, this is LHS, there is an equal to sign here, okay. I just remove this, write it here. I bring this term to my left hand side, okay. I write here M plus Cm of u double dot, okay. Let us keep on checking, this term goes away, this term goes away, plus there is a u dot term with C here, so u dot term with CD here, okay, is negative on the RHS, I bring it to the left hand side, C plus CD of, let us say CD has got a multiplier here, root 8 by pi sigma v of u dot. So let us say this term is gone, this term is gone, plus Ku is equal to one, what we have left over we will take it to the right hand side. So there is u double dot g here which goes there, minus, so minus of M, there is already a minus term on the right hand side u double dot g with Cm, okay, plus Cm of u double dot g there is a negative term here with u dot g with CD. So, minus CD 8 by pi sigma v u dot of g, that is this term. So, I have v dot here with Cm, I have one more v dot with Ca. So, plus Cm plus Ca of v dot, this goes away, and of course one more term of CD 8 by pi with V plus CD 8 by pi sigma V. So, that is my modified equation of motion. It is a classical form how people write equation of motion when the structure or the body is subjected to earthquake acceleration. How do you check that? Whenever there is a negative sign on RHS talking about u double dot g, it is a classical form of writing equation of motion with ground acceleration. So, whenever you see any equation of motion written with ground acceleration, you will find that there is a negative sign on your RHS talks about u double dot. So, it is a classical form which we derive or which we assembled or rearranged from the original equation of motion. This is class A where my structure or the platform is resting on the seabed, where seabed is moving horizontally, ocean does not move horizontally, cylinders will vibrate, will cause vibration, and they will also cause movement, that is neglected. Therefore, radiation damping term is not there in the system, only viscous damping is there. So, classical form of equation of motion for this. Now, once what do we know from this equation and what we will solve? Any questions here? So, what do we know from this equation? U double dot g should be known to you, otherwise we cannot solve this, okay? Forcing function, and of course V, what is V? Water particle velocity or water particle kinematics, we should know this, okay? At any instant of time or at any member position Z from the seabed, I must know V, can use any appropriate theory to get V, okay? We have seen these theories, so I must get V, okay? So, let us see this equation back again. I have this with me. Of course, CD Cm are known to me, I am not talking about that at all, we know this. There are various international codes which will advise me what CD Cm should I use for a depth in variation or what approximate values I should use for a specific sea state, okay, API for example. So, CD Cm is known to me, of course Ca is also known to me, and it is a linearized drag, I know this and therefore I know this also. What I will solve is solve for u, which is actually the displacement of the cylinder. Since I am getting solution for u, actually call this as equation of motion, okay, talking about displacements. So, what I will get here will be the displacement time history will be the outcome, because the forcing function everything is time dependent, okay, V is time dependent, u double dot g, so derivative, so time dependent, I will get the displacement in time dependency. So, how to solve this and what will be the scheme to solve this in time domain, we will see in the next lecture. We will take up a time iteration scheme advised by Newmark's beta method. We will take up the scheme, and there are many other schemes suggested, Wilson theta method, etc. We will look into those schemes in the next lecture and see that what scheme I will apply and how do I actually the scheme makes it iterative. We will see that, and of course we will not solve the problem here, I will show you the results and solutions for this particular case. Any questions here? This is how I am handling problem A, where my structure is resting on seabed and seabed is moving horizontally. Now, there are interesting questions being asked. One, why the vertical motion of the earthquake is not considered? because we are talking about horizontal movement only. Earthquake has 3 direction movements. What are they? Okay, along x, along y and along z. When I am talking about unidirectional force, I will take either along x or along y. I can do analysis in both forms and see which is the maximum response. If you want to combine these two, then IS 1893 says take x plus 30% of y only. Okay, you can combine this also, right. Why the vertical force is not considered in offshore structures? We are talking about this. Why? There are many reasons for this. These are interpretations from the research papers. Okay, many of the discussions what we have in the lecture all here are interpretations and studies made by different researchers. They may not have a direct reference on the blackboard here. Look upon the literature, you will find these are relevant applications done in offshore structures. The main reason for this is remove this. If you look at offshore platforms, let us say which are gravity based or bottom fixed or which are compliant, which in layman language floating, technically compliant, non technically floating. To resist the lateral forces, if you want to bottom found the member will have enormous mass. When the member is having enormous mass, U double dot G in x axis will cause inertia force on the system, U double dot G in the z axis will be counteracted by the mass. Okay. So, the member will have indirect effect, but the mass is very large compared to the amplitude of this motion, need not be considered. If you look at the floating structure, very simple, the mass is very less, but the submerged volume is very high, because they are buoyancy dominated. Okay. The buoyancy domination in these platforms are generally very high. To counteract this buoyancy, I generally hold it down to my foundation using teethers or in a layman's language cables. Inertia forces will be attractive only when they are acting on a respective mass. Okay. Now, teethers will have no mass at the foundation point, and these vertical accelerations cannot be directly imposed on teethers or on the system which is floating, because they are not resting. So, there is an indirect effect caused on the system because of the vertical motion or horizontal motion through the cable or through the teether. So, it is an indirect process, whereas in this case it is a direct process. So, vertical motions are not generally considered in the analysis of, let us say, seismic action for offshore platforms. The second question comes, how do we do this indirect action in a platform which is floating? We will derive the equation of motion for this separately in successive lecture as we derived it for fixed base structures, but the idea is teethers are connected to seabed, seabed moves, that is what we already see. This movement actually changes the tension in the teeth. The change in tension, what I call as delta T naught, the change in tension affects buoyancy. The change in buoyancy affects stiffness in the teeth. The change in stiffness affects force in the body, and this is the force which is directly applied from the earthquake movement to the body. Okay, this is the force. So it is not directly applied, it is indirectly transferred through this mechanism and it is applied. So interestingly, in this process automatically the damping imposed by seawater or water depth is accounted, is it not? So automatically accounted for. How? The damping will reduce the forces on delta T naught, and that will counter affect the buoyancy, and the buoyancy will counter affect stiffness, and stiffness will counter affect the force on the superstructure or on the deck. So the damping imposed by the water depth on floating system because of earthquake action happening in the seabed will be automatically accounted in this mechanism. So it is an indirect method. So it is an indirect method, whereas this is a direct scheme. For a direct scheme, I already had the equation of motion shown to you. I can use any time iterative scheme to solve this and get time history of the displacement of the platform or the structure which is founded in seabed. Whereas for an indirect scheme, we will pick up an example problem and draw or write the equation of motion again, then we will see in stages how the transfer mechanism takes place and what do we actually get at this stage, what will be the input at this stage. We will see that in the scheme. Okay, that is how it is done in case of seismic action applied on as one of the lateral forces which is mandatory for offshore structures other than waves and current. Okay. Any questions here? So, it is already 5 minutes only remaining, or maybe 3 minutes. So, we will talk about quickly at least the conceptual picture of articular tower, then we will move to the dynamic analysis in the next lecture. Okay. So, this is a conceptual picture of articular tower. You may wonder where the tower is. This is the tower actually. Okay. This is the tower which is single legged. Why it is called articulated? There is a hinged joint here. Articulation is a technical name given for a hinged joint. What is the purpose of this tower? This tower will have a deck. You can see here there is a deck here. There is a deck here. The purpose of this tower is to anchor the floating or any shuttle tanker. Okay. It is working as a anchor leg, for anchoring purpose, articulated leg platform, that is ALP. So not necessarily articular towers are used for or implemented or installed for production and drilling, they can be also used for anchoring. So the majority of application of articular towers in the present scenario are used for creating temporary naval base in sea. If you want to create an inspection base in sea, naval base in sea, I go for ATs, because AT installation and decommissioning are as simple as that, and they can be mostly reusable. And if you want to hold down a big tanker in the sea during FSO, floating storage offloading process, to hold it down I have DPS systems, dynamic positioning system. In addition to that, I anchor the shuttle tanker with an AT. The third application is if you got deep water risers where the direction drilling is taking place, in between the riser segments I have to hold down the riser profile, otherwise risers will be subjected to lot of lateral forces because of current and waves. To avoid this or to improve on the dynamics of risers, I support the risers in between using this kind of structures. Okay, there are segmental applications for this. Obviously AT cannot be a production platform, but surprisingly ATs have been also attempted as production platforms, which I will show you in the next lecture. Okay, couple of production platforms have been attempted in US and Gulf of Mexico as using multi-hinged, multi-legged ATs, okay, MLATs. Okay. Why I picked up this example is that ATs has got a very high degree of freedom in terms of response, rotational response. So people now start working on controlling this response using some artificial networks or some artificial techniques, where they called as response control algorithm for articulate towers. So we will pick up that example as extended study of this in the due course of lectures. So we are going to talk about ATs in the next lecture. So conceptual figure, of course displacements of ATs are governed by the rigid body vibration of very low frequency, that is very important. Since there is a low frequency mentioned here, wind energy or wind spectrum which has got high energy, the low frequency will be predominant. So they are more versatile and susceptible to wind action apart from waves. So wind forces are low frequency phenomena, therefore wind velocity spectrum has a very high energy content at the low frequency, therefore aerodynamic response of ATs become more critical. But essentially we have seen in the first module, ATs derive stability because of large buoyancy forces. We have got buoyancy tanks based on which ATs actually derive the stability against lateral movement. Okay. So the fundamental period of vibration of ATs become very critically important in our analysis. This gives actually rise to a rigid body motion which vibrates only in a specific frequency, okay, as expressed by Jain and Datta in 1990. I think we will stop here, we will continue with the next lecture. We take up the mathematical model of an AT, we will show you the solution. We will not solve it here, of course, it is not possible. I will go discuss the results of this particular structure in dynamics perspective in the next class. Any questions, any observations in this lecture?